I'm very thankful to the organizers for giving me the opportunity to present my work in this conference. So today I'm going to speak on enumerating alternating runs with sign in type A and type B obscure groups. So this is based on joint work with Shivaramakrishnan and Shivasubramanian. So let Sn be the symmetric group on n letters 1 to n. Any function from Sn to the set of non-negative integers, we call that a permutation statistic. So why are we interested in permutation statistic? So firstly, permutation is a fundamental combinatorial structure. We study them for fun also, and they appear in different contexts. So we see some examples of permutation statistics. So for a permutation pi, written in one line notation, the descents of pi is the set of descent is a set containing those indices such that pi I is greater than pi I plus 1. And base of pi is the cardinality of this set. So pi equal to 314526. So there are exactly two positions, namely 1 and 4, such that pi I is greater than pi I plus 1. So the descent set is 1, 4, and the number of descent is 2. Inversions of pi, another very well studied statistic, is the inversion of pi. So which is the number of ordered pairs ij such that I is less than j and pi I greater than pi j. A number of inversion is cardinality of in pi. So in this example, this permutation pi has four inversions. So for any statistic stat, consider this polynomial summation pi in Sn minus 1 to the power inversion to the power state of pi. For a permutation pi, the sign of pi is defined as 1 if it belongs to the alternating group n, and minus 1 if it belongs to the Sn minus a. So one can note that the sign of pi is nothing but this minus 1 to the power n. Now, enumerating various statistics under sign is a very well studied problem. So there has been a lot of works on enumerating sign statistics. So this is useful because this gives information about the distribution of a statistic about the alternating group n if we know some information about this over S. So that's why it's very useful. So we mentioned some earlier works. So Fortin and Deschamenier in 1992 worked on sign descents. Mantecchi gave an explicit formula for sign exceedances. Adin, Gesell, and Reichman gave explicit formula about sign Mahonians. And most of the time, the sign descent, sign exceedance, signs Mahonian, they have very neat and very elegant factorization formulas. So there have been many other works. So in this work, we are interested in alternating runs. So what is an alternating run? So for a permutation pi in Sn, so the set of peak of pi, the set of peaks. So it is those indices I such that pi I, this value is greater than its predecessor and also the successor. And value is just the other way around. So those indices such that the value at the ith index is less than its predecessor and successor. So let peak and pi is the cardinality of the set. Peak pi and val pi is the cardinality of value. And if we draw a permutation, then we can see that it changes direction at I if I belongs to P, pi or val. So we say that pi has k alternating runs denoted by all trans of pi equal to k if pi changes direction at k minus 1 axis. So for example, this permutation pi equal to 2314675. So there are exactly two peaks, namely 2 and 6, because pi 2 is 3, which is greater than 2 and 1, and pi 6 is 7, which is greater than 6 and 7, 5 and 7. And it is exactly one value. So pi 3 is 1, which is less than pi 2 and pi 4. So the number of alternating runs, so if one draws, then one can, so there are 4 runs. So it has 4 alternating runs. So the alternating runs polynomial is defined as the generating function of alternating runs over the symmetric group. And Rnk, so this is same as summation Rnk to the power k. So several formula for this Rnk exists. So Stanley in 2008, Canfield and Wolf in 2008, and later Mai in 2012. So they have presented explicit formula for this coefficients Rnk. Here we are interested in enumerating alternating runs in the alternating. So we are interested in looking at the polynomials Rn plus t and Rn minus t. So where Rn plus t denote the alternating non-enumerating polynomial over the even permutations, and Rn minus t denote the alternating non-enumerating polynomial over the odd permutations. Okay. So towards that, so let us define the signed versions of those polynomials. So signed alt run nt denotes the summation minus 1 to power n y to the power alt run phi. And signed alt run in pq, that is the summation minus 1 to the power n phi, p to the power p pi, q to the power phi. So one can note that the sign alt run nt, that is nothing but t into sign alt run n pq. And here we are setting, this is evaluated at p equal to q equal to. How is this actually working out? Because so what is the alternating runs? The number of alternating run is same as the number of peaks plus number of valleys plus 1. So this t is coming for that extra one, and that's it. Okay. So we're interested in the sign enumeration of sign bivariate peak valley polynomial. So our result is when n equal to 4k and 4k plus 1, then it neatly factorizes into 2 into 1 minus p into 1 minus q into 1 minus pq to the power 2k minus. And when n equal to 4k plus 2 and 4k plus 3, this signed enumerations are 0. Okay. So we will give a brief idea of our proof here. So our proof actually uses two easy bijections from a principle. So firstly, the complementation bijection. So as the name suggests, it takes a permutation to a complement. So you take pi 1, pi 2, pi and to n plus 1 minus pi 1, n plus 1 minus pi 2, and going up to n plus 1 minus. So one can see if one does this, so it switches the peaks and valleys. So if pi has some peaks, complementation of pi that has peaks at exactly those, that has value as exactly those places. We are also define another bijection which is called the reverse bijection. So it takes pi 1, pi 2 up to pi n pi n minus 1 going to pi. Now, one can see something about this reverse bijection. It maintains, so the number of peaks and the values of pi is same as the number of peaks and the values of reverse of pi. And it changes the sign. So by the reverse bijection, for n equal, it changes the sign when n equal to 2, when n equal to 2, 3 mod 4. So by this reverse bijection, we are immediately done when n equal to 2, 3 mod 4. So when n equal to 2, 3 mod 4, as this changes the sign, hence this gives that the sign enumeration is nothing but C. Now, when n is 0, 1 mod 4, then our thing is much more involved. Actually, there, our idea is we are interested in the starting to or the ending. So there are 4 options for this. The starting thing can be increasing, and the ending also increasing. The starting increasing, the ending decreasing. The starting decreasing, the ending increasing. Both the starting and the ending decreasing. So we actually partition Sn based on this. And that actually breaks this into the following 4 sets. Now we enumerate the contribution to the signed alternating run polynomial from each of the 4 sets. And over each of the 4 sets, we do that recursively using the earlier bijections. And using these recursions inductively, we prove work. So that's the idea of our. Now we see some applications of our. So while in 2000, Wiles actually gave in long back. So proof that for every positive integer n greater than equal to 4, the polynomial Rnt is divided by 1 plus t to the power a. So it's divided by a large power of r plus t. And Bona in 2021 gave a beautiful combinatorial proof of this. It's very beautiful. He gave a beautiful group action based proof of the same fact. So using our result, we can immediately show that for positive integers n greater than equal to 4, when n equal to 0 and mod 4, these polynomials Rn plus minus t, they are divisible by 1 plus to the power m minus 1. That is roughly n minus 2 by 2. And when n equal to 2, 3 mod 4, they are divisible by 1 plus to the power I. But our proof follows as an application from the signed enumeration. We were trying to give a combinatorial proof along the line of Mona, but we are not able to find one. And it would be very interesting to get a combinatorial proof of this. Now, this Chava and Ma in 2014 proved that the following identity, that 1 to the power k Rn, 1 plus 2 to the power k Rn 2 plus dot dot is 2 to the power k Rn 2 plus 4 to the power k Rn 4 plus. And so from signed enumeration, it directly follows that this will also hold for the plus minus alternating run coefficients. Now we have seen alternating runs, alternating group, and now let's go to alternating permutations. So permutation is said to be alternating if the first index is greater than the second is less than third is greater than fourth, and so on. So it is pi I less than pi I plus 1 for even indices I and pi I greater than pi I plus 1 for odd indices I. So for an example, 2, 1, 4, 3, 5 is an alternating permutation. So 2 is greater than 1, 1 less than 4, 4 greater than 3, 3 less than 5. But 2, 1, 3, 4, 5 is not. Now let this alternating run all 10. So that denotes the set of alternating permutation. And let En counts this. So Andre proved that En is the number of alternating permutation in Sn. Then the exponential generating function for En, that is same as summation En x to the power n by n factorial. That thing. So that thing is actually nothing but a beautiful thing. That is sec x plus 10. So the exponential generating function for En is sec x plus 10. So we're able to actually find a refinement of this. So if En plus and En minus denote the number of alternating permutations in even in the alternating group and the complement of alternating group in the symmetric group, then summation En plus minus x to the power n by factorial is half into sec x plus 10x plus minus cos x plus minus x. So we are also able to find signed alternating run enumerating polynomial for type B and type D Coxeter groups. Here I am not including this for the sake of time, and we are also able to find those similar applications for those polynomials. Thank you.